lecture on photocatalysis and photoelectrocatalysis for solar-driven water splitting.
That's right. So, thanks a lot for the introduction. Let me see if I can get the microphone working. All right, let's see, is that loud enough? Or does that seem okay? Okay. So I've maybe split up my presentation this morning in a little bit different way than was implied by the title that's on the printed program, and we'll talk first about electrocatalysis and then about photocatalysis in the second session this morning. And try to relate this to the general area of catalysis for renewable energy applications that we talked about yesterday. Right, so again, just to kind of retrace where we were, right, most of today's energy economy is built on fossil fuels, and the advantage of fossil fuels is we can do some relatively simple upgrading techniques to convert those sources of carbon into useful molecules with, for example, high octane or high cetane numbers in order to use those as fuels. And we can also reform them, although we didn't talk about this as much, to make hydrogen, for example, for use in hydrogen fuel cells. But as we talked about yesterday, we also might want to look at alternative sources of carbon. And one alternative is biomass. And the real issue with biomass is we can make some of these same kinds of fuel products, but we have to extract a lot of the oxygen that's inside those the biomass precursors. And doing that involves different types of catalysts that are typically used going this direction. All right, so what we'll talk about today are things more centered on hydrogen fuel cells, which have some inherent large efficiency advantages, and especially if you're going to use hydrogen as a fuel for automotive and stationary power applications. And we'll tie the reactions that happen here actually to what would happen in a photoelectrochemical cell. And then in the second session, we'll talk explicitly about some of the catalysts that can be used in those kinds of cells. Okay, so that's where we're headed. What I hope to cover in the next few minutes is how electrocatalysis differs, the reasons why it might differ from traditional heterogeneous catalysis of the type we talked about yesterday, what sort of catalysts and reactor geometries are used for fuel cells, what are some of the challenges with trying to study the surface reactions when you have an electrified interface as you do in an electrocatalyst or a photoelectrocatalyst. And then what can we do to improve catalysts from a rational basis? And here we'll invoke Sabatier's principle that we talked about some yesterday. Okay, so let's take a look at a simple diagram showing what happens in a fuel cell, and we'll focus pretty much exclusively on hydrogen fuel cells. If there's time at the very end, I might talk about a couple of other types. But hydrogen fuel cells are useful for us to talk about because we're going to ultimately be interested in the next session in water splitting, and that is exactly the reverse process of what we're showing here. So a lot of the same catalysts, in fact, can be used for either application. Okay, and so in a hydrogen fuel cell, you have your fuel side, and that fuel in this case is hydrogen. And then you flow in hydrogen, and you have hydrogen that will react on the surface of a catalyst. That catalyst in most commercial fuel cells that you can get these days is a supported platinum catalyst. So platinum supported on carbon actually, because you need an electrically conducting support. All right, the hydrogen dissociates and makes hydrogen atoms, and then ultimately you get a charge separation reaction to make protons and electrons. And the electrons flow through an external circuit and do your work. All right, so that's your electricity that powers your automobile, for example. Your hydrogen, in this case of a PEM fuel cell, the protons actually go through this electrolyte material, which is typically a solid polymeric electrolyte. So Nafion is the most common one used today. It basically promotes acidic transport across this membrane, but the membranes are electrically insulating, which is why the electrons flow through the external circuit. The electrons then recombine with the protons and oxygen that's coming from your airstream that's being fed in order to do this reaction, which makes water. All right, it turns out, and there's something very similar that you see in dealing with water splitting, is that this reaction is pretty easy to do. All right, so you don't need all that much platinum, and you can split hydrogen to make protons, and that works pretty well. All right, this reaction turns out that it has these 4 electrons and 4 protons being added. It's hard to do, and there are really 2 key issues in getting fuel cells to be more economical and therefore more viable in the long term. And one of those issues is that this reaction is not fast enough. And if it's not fast enough, that means you don't have enough current going through to drive your automobile, for example. Right? Since the rate at which this reaction takes place is directly related to the current that you're producing. Okay, and the other big problem that we won't talk about today that people are working on is trying to improve this electrolyte membrane. That currently it's very expensive, very fragile material, and so people are working on trying to make membranes that can last longer and be more durable, and most importantly be a lot cheaper, hopefully orders of magnitude cheaper than the current membrane. And another disadvantage of the current membrane is that you have to keep it very hydrated in order to transport protons and keep it from becoming overly brittle. So you have to feed a lot of water into the reactor during the reaction. And so those are really the 2 key issues, and we'll focus, since this is a catalysis presentation, mostly on the fact that this reaction is slow and what people are trying to do about it. Okay, so the next 2 slides, if you're going to tune in for just a couple of slides, these are probably the 2 that they are very closely, they're very relevant for really everything that is going on in electrocatalysis and photoelectrocatalysis. So it describes sort of the fundamental problem that we're dealing with. And so if you want to we'll look at this first from the perspective of a hydrogen fuel cell, and then we'll talk about kind of the opposite case where we're trying to do water splitting. Okay, so if we have a hydrogen oxidation reaction, so H2 going to make protons and electrons, which was on the left-hand side of our device, all right, there will be some potential, some charge that we place on the electrode at which the forward reaction will happen at the same rate as the reverse reaction, so which will be at equilibrium. And both reactions will still be happening, right, but they'll be happening at the same rate. And so what you're basically doing by changing the voltage that you apply to the electrode is you're changing how happy the electrons are being in the electrode, so how happy these products are. And so by shifting the voltage, you can shift whether the driving force is in the forward direction or the reverse direction, or if you find the happy medium, which we're going to define arbitrarily as being at 0 volts, then, because this is the standard hydrogen electrode basically, that you get equal rates in both directions. Okay, and the same is true for the oxygen reduction reaction. All right, here the equilibrium potential is higher. All right, and in the sign convention that we use here, this means that the electrons are happier being here, which is why they're going to flow to this electrode in a fuel cell, that they're going to want to come to this electrode because they're happier being at this electrode. All right, then the 4 electrons can react with the same rate in the forward direction as the reverse direction if we bias the device 1.23 volts with respect to the electrode on the other side of the fuel cell. All right, then everything will be in equilibrium. All right, but of course equilibrium isn't really what we want. What we want is to drive the reaction in one direction or the other. We either want to make this reaction go in the forward direction to produce water and electricity, or when we're dealing with photoelectrocatalysis, we're going to be wanting to basically generate electrical currents with the photoactive material and drive the reaction the other way, right, and not have it be at equilibrium. Okay, and so if we want to do that, right, this is sort of a useful plot to look at, and I apologize for these variables, which we won't get into the details of, but this is basically just the voltage that we're applying to the electrode, and we'll focus just on the cathode for the oxygen reduction reaction. All right, so this shows the Gibbs free energy change as we go from reactants to products. Okay, and the idea here is that you can make these equal if you apply 1.23 volts. That's basically this distance here. You can make the Gibbs free energy of the reactants and the products equal. All right, and so by shifting the voltage, you can shift whether the reactants are above or below the equilibrium potential, or their equilibrium. Excuse me. You can control whether the Gibbs free energy of the reactants is above or below the Gibbs free energy of the products, and therefore either derive the reaction in the forward or reverse direction, since the reaction is always going to want to go in the direction of decreasing Gibbs free energy. All right, if we want the reaction to go in the forward direction, so if we want to do oxygen reduction, then we need to apply less than 1.23 volts. All right, and so we want to apply as close to 1.23 as we can while still getting a good rate of reaction, because the higher the voltage, the higher the power we're going to get out, since power is equal to voltage times current. All right, so we want as high a voltage as we can get, but it's going to have to be something below 1.23 volts. All right, and the difference between 1.23 volts and the actual voltage that we can get is called the overpotential. And that's the number one problem in catalysis for oxygen reduction or water oxidation. All right, it's trying to minimize the overpotential while still getting good current going through your device, still having a good reaction rate. Okay, if we want to do water splitting, then we're going to have to do something greater than 1.23 volts. Right? Because we're going to want to drive the reaction in the opposite direction. All right? And so what this points out is that you're never going to do as well as the ideal. Right? Of course, you want to try to minimize the voltage that you have to apply in a photoelectrochemical device where you're having to do work by providing sunlight, basically, and generating electrons and holes, as we'll talk about in a few minutes. All right? And so you want sort of the minimum that you can get here. All right, but 1.23 is the best that you can do. All right, and you're going to have to have some voltage greater than that. And you'd like to have the maximum when you're doing the forward reaction, but 1.23 is the best that you can do. You will only be able to get something less than that out of the device. Yeah.
We just got an email from a webcast viewer that the sound is not very good.
Okay.
Maybe you could use this microphone because it's connected directly.
I see. It's okay. I don't know if I have some setting on this wrong. Where should I stand? Okay, is that, yeah, let's see. I can actually stand pretty far away, it seems like. Okay, so any questions about that principle? Okay, so this is going to be coming up kind of over and over, and we'll come up again. We're going to look a lot at, stand further away, look a lot at the importance of this 1.23 volts and deviations from it, especially when we get into the water splitting section. We'll see that we need a band gap of at least 1.23 volts in our materials. Okay, so how does the fact that we're doing electrocatalysis, how does that change the way that reactions occur on surfaces? Okay, so now we're dealing with charged species, whereas before when we were talking about petroleum refining and biomass refining, the species typically were not charged that were involved in those reactions. All right, and it turns out that really has a profound effect on the way even simple reactions occur. So if we look, let's say that we were going to take a platinum catalyst, which is an excellent catalyst for this application, and we want to burn hydrogen. So we're just going to feed in oxygen and hydrogen over a platinum catalyst and not set it up as an electrochemical device. All right, in that case, what happens is that reaction will go extremely fast. Okay, and the oxygen will dissociate to make 2 oxygen atoms on the surface. The hydrogen will dissociate to make, if you take 2 hydrogen molecules, 4 hydrogen atoms on the surface. And then you get sequential addition of H to the O's to make OH, hydroxyls, and then finally to make water. And that reaction is very, very, very fast, dangerously fast on platinum catalysts. So I was in a lab once where they accidentally fed this mixture to a catalyst, and it completely, temperature got into 1,000 degrees C, and it melted the reactor. So the reaction really goes. All right, unfortunately, this reaction in an electrochemical type environment doesn't go fast enough on a platinum catalyst. All right, and the mechanism is very different. So the oxygen will come in and bind on the surface, and then what you actually have in an electrochemical system, instead of having hydrogen being added during the oxygen reduction reaction, you have proton and electron pairs that are coming from different places, remember. The electron's going through that external circuit, the proton's coming through the membrane, coming through the electrolyte. And they form this peroxy intermediate, OOH. Right, and then that peroxy intermediate subsequently dissociates. And then the chemistry looks more similar to what you see up here, that you get sequential addition of protons and electrons. Right, and then in an undesirable reaction that we won't talk about much in here, you can also get hydrogen peroxide formation, which degrades the catalyst, and particularly the electrolyte connection to the catalyst, and is therefore a very undesirable product. Okay, so we see that the mechanism is very different, and so the question is, why is the mechanism different? Why does having these charged species, why can't the charged species come down and just interact with the surface and form something more like an H that then reacts with the other species on the surface? Okay, and there are basically a lot of the research over the last 6 or 7 years is focused on trying to elucidate those features that make electrochemical reactions different. And there are basically two main effects that have been probed in those studies. And the first of those is the fact that, okay, we have a charged surface here. It's a positive charge that's causing electrons to want to go there in the case of the oxygen reduction catalyst, in the case of the cathode. All right, and so because this has a positive charge, you have a thin layer of liquid in practice over the surface of the catalyst. And there will be charges that accumulate close to the surface in the liquid that preferentially orient a more negative charge in the solution phase. And so because of that, you have a large electric field of about 0.5 volt per angstrom. So a huge electric field, actually. If you change this to something that we're more used to, like centimeters, and you see that it's an enormous magnitude. And so the first hypothesis was that these electric fields would actually have a very large impact on the way the reactions took place on the surface. All right, but I'll show you a little bit of that work, but it turns out that that's not the case. Right, that actually doesn't have a very large effect on the way that reactions occur on the surface. And what has a much greater effect is the fact that you have this solution layer here, you have water, and it's highly oriented because of this dipole moment that it's going to tend to be, or because of this electric field, the water's dipole is going to want to align the molecule like this. And it's going to form extensive hydrogen bonding networks with any hydrogen-containing species on the surface. And that's really going to affect the way the reactions take place on the surface, compared to if you don't have those hydrogen bonding interactions. Okay. So we'll look quickly at some of these effects. Right, it turns out the nice thing about electric fields is that there's a very rigorous theory that you can develop that explains how electric fields should affect reactions. Right, and actually a very simple level of theory explains, for the most part, what they do. And that's simply what's referred to as a first-order Stark effect. Right, and so if you have a certain energy for the interaction between an adsorbate, like say oxygen, and the surface, and you vary the electric field, right, that energy should change in proportion to the dipole moment. Right, so if you have a dipole moment associated with your adsorbate, if you impose an electric field in the opposite direction of that dipole moment, it'll stabilize that dipole associated with the adsorbate. Right? But if you apply the electric field in the opposite direction, that decreases the stability of the adsorbate. Any questions about that? All right, and so that's totally predictable based on the field strength and the dipole moment. And so you can actually do experiments. These are based on density functional theory calculations. And you can see that basically as you vary the electric field strength, these are the points that we're measuring the interaction energy of oxygen, both adsorbed O2 and adsorbed atomic oxygen. And we see that they follow these predicted first-order Stark effects very well. So by just knowing the dipole moment of the adsorbate, so how the charge is distributed between the adsorbate and the surface, you can predict the effect of electric fields very well. All right, you notice that there's a small amount of curvature here, right, especially for O2, and you can predict that effect based on the polarizability of the molecule, so its response to the electric field. And so you can actually do an extremely good job of modeling how an electric field affects surface chemistry. Right, but we won't get into that today. Okay, so we see that we can predict what happens with an electric field. And so now it's useful to look at how this affects something like the dissociation of molecular oxygen during the reaction. Right, and we see this is the case, this is the energy barrier with respect to what you would have under neutral conditions, so at 0 volts where you have no electric field, right, compared to where you have an electric field of what you typically would see at a cathode in an oxygen reduction reaction, right, which is 0.5 volt per angstrom. And we see that the dissociation barrier goes up by less than 0.1 eV, right, which in a catalytic system is, it's a significant difference, but it's not a huge difference. It really can't explain why the oxygen reduction reaction is so much slower. So it's a pretty small energy difference that's a result of these electric fields. All right, what's more important, and there have been a lot of studies of this over the last 5 years, is how water interacts with various adsorbates. And this shows sort of what a solvated proton would look like at a surface. Right, so this is an H atom. You can actually do an experiment and put H atoms down on platinum 111 and dose water, and you see that you form this kind of Zundel ion, which is a proton that's solvated by 2 water molecules. Right, and so you can look at the way that these Zundel ions interact with important species on the surface like O2, and you can see that Damjanovic pathway that I showed earlier is the one that is energetically preferred, right? So that you undergo a proton transfer, a shuttling of the proton to form a peroxy intermediate when you have lots of water around. And that's favored over sequentially adding adsorbed atomic H that they would rather add as a proton through this kind of very conventional proton shuttling mechanism. And you don't get direct dissociation of oxygen. That's disfavored actually by the hydrogen bonding network that's set up. And then we can probe the dissociation, for example. We see that the peroxy dissociation is the next energetically preferred step, and that on flat terrace sites, actually, you don't form much hydrogen peroxide, and that's mainly on the defects. The subsequent steps are maybe a little bit easier to understand. I won't talk about those. You just get proton transfer to O, and then proton transfer to OH to ultimately make a water your water molecule. And then if you were doing water oxidation, so water splitting to make hydrogen and oxygen, this would just all be in the reverse direction. So any questions about these two effects, the idea of the electric field versus solvent effects? And we'll talk more about solvent effects probably at the end of the photoelectrocatalytic section. Okay, so that's kind of what is happening in this system that's different. All right, electric fields which have a fairly minimal effect, and interactions with solvents which have a major effect. All right, how are we going to make the situation better? How are we going to design a catalyst that is either better than platinum, that would be ideal, or at least that uses a lot less platinum or uses a less expensive material than platinum? Because we can use platinum to get very good power densities in fuel cells, but you just have to use a whole lot of it. And so there was a number, I think it's improved, but a few years ago, that if you equipped 20% of the United States vehicle fleet with hydrogen fuel cells, it would use up all the platinum in the world, including what's already in our catalytic converters, for example. All right, so we clearly have to find a way to use less expensive materials or use a lot less platinum. And the way that a lot of people have been looking at this reaction is in terms of the sort of volcano plots that we talked about yesterday with Sabatier's principle. And so the idea here is that if adsorbates like atomic oxygen and hydroxyls that are formed during the reaction are adsorbed too strongly, then again they're going to choke off the surface and the reaction is not going to be able to proceed, just like we talked about yesterday. Right, so the reaction won't be able to go because the surface is already crowded with adsorbates that are too happy being there. And you'll see that most of the materials kind of fit that, most of the pure metals fit that description, that they're binding things. Negative means stronger adsorption energies. They're binding the intermediates too strongly, and so the surface is just getting self-poisoned with all the intermediates from oxygen reduction. Right, if we're over here with, say, gold and to a lesser extent silver, right, then the intermediates are bound too weakly, so they never really want to form on the surface, and so you can't get the reaction to occur. And so what we want to find is something that's optimal, and platinum is near the optimum, but not quite at the optimum, where you have the intermediates favorably interacting with the surface, but not choking off the reactivity. And so that's what a lot of the research efforts are directed toward, is finding those kinds of materials. Okay, and there's a general rule of thumb here if you're looking at the pure metals. So this is just the transition metal section of the periodic table, that as you move to the right from platinum, then the metals become less reactive. They bind intermediates more weakly. Right, so you have that problem. You're on the right-hand side of the volcano curve. And if you move to the left and up, then the metals are too reactive. So they have electrons that are you increasingly are having more unpaired electrons as you move in this direction. So they're less happy being in the metal, and they want to go out and form very strong bonds with adsorbates, and that chokes off the reactivity of the surface. Okay, I think we may have talked about a lot of this already. So one thing that's definitely observed is that, so atomic oxygen can be a problem. What's been seen in situ spectroscopic studies is that it's really the hydroxyls that accumulate on the surface and choke off the reactivity. And so a lot of the effort has been devoted to finding ways to destabilize hydroxyls on the surface so that you favor them going on to form water. Okay, and so I think I had this plot up earlier but forgot to talk about it, so it's good to put it up again. Okay, the way that the slow kinetics of the oxygen reduction reaction manifest themselves is that, as I mentioned, the best that you can do under pH neutral conditions is 1.23 volts. As you increase the pH, it actually, I think this is an increased pH, you decrease that equilibrium potential. All right, and so, but we're still well below the equilibrium potential. All right, and so as you increase the current density, so how much of the reaction you're occurring, you get this very steep drop-off in the voltage that you can achieve across your device, which of course limits your power density. And what you'd like to have is a line that goes straight across so you can operate at high currents and still have high voltage so that you have good power. And so the reason that this drops off like this is because the oxygen reduction reaction is slow. And so to get high rates, you have to have a high overpotential, so a very strong driving force for the reaction in terms of the Gibbs free energy, as we talked about earlier. I think I'll cover that in another slide. One thing that's observed in the oxygen reduction reaction that's kind of unfortunate, right, is that the fastest reaction rates on a per surface area basis occur on the biggest particles of platinum, the biggest crystallized that are on the surface. And that's a really bad thing from a cost perspective, because that means that you have lots of platinum atoms that aren't on the surface and are inside your bulk and therefore aren't able to participate in the reaction. So that makes it a very expensive catalyst. And the smaller particles that have a lot of the platinum atoms on the surface that you'd really like to use have a much slower rate associated with them. Okay, and the reason for that is related to something that we talked about yesterday, is that small particles have a lot of corner and edge sites on them, so they don't have a lot of very open, flat planes of platinum on the surface. And so those, as we talked about, those edge sites are very reactive. They bind intermediates very strongly because they're coordinatively unsaturated. And so since they're binding those adsorbed intermediates so strongly, they're on the left-hand side of the volcano curve, and you don't get a fast enough reaction. Okay, and so you'd like to be able to have platinum atoms that are in a flatter surface in order to have more weakly bound surface intermediates. Okay, that makes basically the same point, and I'll sit down to that. And so there are two ways to do that. As I mentioned, you can use the large particles so that you can get good power densities, but that's going to be a really expensive proposition. And the other thing that people are doing is using platinum alloys, or maybe it would be better to say platinum bimetallics, that in a lot of cases they're not true alloys, that they don't involve mixing between the platinum and the other components. But bimetallics can be used in a couple of ways that we'll try to show. All right, one thing that you can use platinum bimetallics to do is to change you can dope in just a little bit of another metal that will change basically the lattice structure of the metal. All right, and so you can try to, for example, either decrease the average distance between platinum atoms at the surface or increase it. And if you decrease it, then what you're basically doing is you're sort of artificially increasing the strength of the interaction between these two platinum atoms. And so you're going to bind adsorbates less weak or less strongly because of that. Right, so stronger interactions between the platinum atoms mean weaker interactions with hydroxyls that are poison in the reaction. So that's generally what you want to do. Whereas if you expand the lattice, now these platinum atoms are not interacting as strongly with each other, and so they're going to want to interact more strongly with adsorbates, which is not what you want in this case. In this case, remember, we're on the too strongly interacting side of the volcano curve. Okay, and so people have used a variety of different metals that they dope in with the platinum, and they can see that as they change the nearest neighbor distance to be shorter, then they get a higher activity for the catalyst, right, in line with this. And a nice thing about doing theoretical calculations is that we can just arbitrarily specify the platinum-platinum nearest neighbor distance in a simulation. Right? We can make it not the equilibrium distance, but actually shorten it artificially. And we see that you do, in fact, get a strong stabilization when you expand the lattice and a strong destabilization when you contract the lattice. Okay, so that's using bimetallics that really form alloys. Another strong area of research is trying to use coarse shell particles. And so remember, what you want is a lot of terrace sites and not very many corner sites. And one way to do that is to use a very large platinum particle. But another thing you can do is use a cheap metal in the core, like nickel is often used, and then try to coat platinum around the outside edge. And this actually works very well. You can get very good activities with pretty minimal platinum loadings if you use these kind of coarse shell particles. The problem with these are they're very questionable, might be putting it nicely, their instability over long periods of time. So they'll work for periods of hours, but you get restructuring. This is not a thermodynamically stable structure. You're going to want to have mixing between, for example, nickel and platinum. And so the nickel will start to come up into the surface, and it actually will get leached away by the solution. But the nickel is not very stable when it's exposed at the surface. It likes to be pulled out by the acidic solution. All right, and so people are looking at ways still of trying to really stabilize these and find core materials that might work better. But the long-term tests so far don't look very good. Okay, another thing that people have done is try to look at more thermodynamically stable systems that you can design to do what you want. I won't go into the details of this slide because I want to finish up with enough time to address any questions. But one thing that people have done is try to select a second metal, right, that will come to the surface. And sort of counterintuitively, they've chosen metals that bind hydroxyls very strongly. And it turns out that this can be a good thing because the hydroxyls that are bound on this second metal, which is shown in green, right, will tend to repel hydroxyls that would accumulate on the platinum atoms that are really doing the work of the reaction. Right? And so you can, by having hydroxyls on the inactive part, you disfavor a lot of accumulation of hydroxyls on the active part of the catalyst, which is the platinum. Right, and so this seems like, so far, I don't think it's been subjected to a lot of long-term tests, but it seems like a promising direction to go. Right, and then maybe even more promising is that just last year, and I should have the citation up here, but I guess I don't, a group from Argonne National Lab looked at how to form alloys that are inherently stable under operating conditions. And so they would look as one of their metrics, using density functional theory calculations, at how strong the energy was for forming the particular alloy. And the more negative it was, the more likely it would be in a very strong thermodynamic well and therefore be stable over long periods of operation time inside a fuel cell. And so that they were able to couple that with the analysis of how strongly absorbed the oxygen was compared to what the case is on platinum. And if you remember, what you want to do is just destabilize the case on platinum slightly. Platinum's a little bit on the left of our volcano curve, of our Sabatier plot. And so we want to destabilize that by about 0.2 electron volts. And so what you're looking for are things in this region, and they've shown, at least over, I can't remember how long they ran the test, that they can make some of these bimetallic catalysts, and they're stable over the period of, I think, weeks without deactivation, and also have improved activity compared to platinum. Okay, and so there's still a lot of work going on in this area, And a lot of it we'll see platinum showing up again when we look at photoelectrocatalysis, that it often is doped into photoelectrocatalysts like titanium, for example, to improve the activity, because it is so good at both the forward reaction of oxygen reduction and the reverse reaction of water oxidation. It's not optimal, as shown here. These materials are more optimal, and it's especially not optimal from a cost standpoint. So I think one of the big directions in research right now for both that is really the subject of study for fuel cells, but I think will increasingly be important for water oxidation in photoelectrochemical cells, is using materials that kind of are in this region that don't involve platinum at all. So that involve much cheaper combinations of metals in order to do the reaction. Okay, this actually shows some of their activity at different potentials and shows the improvement. So let's go with that. I think we have just a minute left. I'll just mention there's another kind of or there are many other kinds of fuel cells actually, but there's another one that's receiving particular attention, and that's a solid oxide fuel cell that's used for more stationary power applications. And in that kind of fuel cell, you have oxygen dissociating, and then it actually migrates. You have an oxygen conducting electrode that's usually something like involves doped yttrium stabilized zirconia, for example. It will conduct oxygen that reacts with the hydrogen to make water. So you have sort of a different species being conducted. You still have electron flow occurring outside the device to provide power. And I'll skip that for now. And so I'll just put up my conclusions. I think we have maybe a few minutes left for questions before we go into, take a break and go into photoelectrocatalysis. But any questions at this point?
Any questions for Will? We save them up for the second lecture.
I guess so.
Okay. Well, in that case, I think we will break. We're a little early, but that's good.
Yeah.
More time for coffee.
Yeah. Sounds good.
Can we join in thanking Will for his presentation? So the plan is to reconvene. If you could just move the second one, put the glasses on. If we could reconvene at somewhere around